This video covers 20 most important questions of hydrogen based on JEE, Neet and even JEE Advanced examinations. This will briefly cover the entire chapter. Let's start. First question. Which of the following processes uses water-gas shift reaction for industrial preparation of dihydrogen? Water-gas shift reaction for industrial preparation of dihydrogen. The options are Merck's process, Lane's process, permuted process, and Bosch process. Now, one by one, we'll discuss these processes and finally come to the answer. Merck's process is the preparation of hydrogen peroxide from sodium peroxide. So, when sodium peroxide is acidified with H₂SO4, sodium ion gets converted to sodium sulfate and the peroxide ion gets converted to hydrogen peroxide. So this is the preparation of H₂O₂. Lane's process. Lane's process is preparation of dihydrogen using Fe and steam. So Fe, when heated with water, gives Fe3O4, that is magnetite, and liberates dihydrogen. But this is not the water gas shift reaction. Third, permuted process. Permuted or zeolite process is the process for removal of hardness of water using zeolites, which is nothing but sodium aluminosilicate. So the zeolite Z is nothing but Al2Si2O8.xH2O, and these zeolites exchanges the calcium and magnesium ions in hard water to form calcium or magnesium zeolite and exchange the sodium ions. So this is the process for removal of hardness water and not the preparation of dihydrogen. Next was Bosch process. Bosch process is nothing but water gas shift reaction wherein carbon is added with water at 1270 Kelvin to produce water gas, which is mixture of carbon monoxide and dihydrogen. This water gas is further added with steam in the presence of Fe2O3 and Cr2O3 at 773 Kelvin, where the carbon monoxide oxidizes to carbon dioxide and H2 is liberated. So this is the industrial preparation for dihydrogen and it is called Bosch process or water gas shift reaction. Now, to obtain pure dihydrogen, CO2 can be removed by dissolving in water, thereby getting H2. So this is Bosch process. It is also called coal gasification or water gas shift reaction. CO2 is removed by dissolving in cold water by upward displacement of air or by absorbing in alkali KOH or by scrubbing it with sodium arsenide solution. So it is removed by dissolving in cold water because CO2 is soluble, and is removed by upward displacement of air because CO2 is heavier or more denser than air. It can be removed by absorbing in alkali because CO2 is an acidic oxide. It can also be removed by scrubbing with sodium arsenide solution, and here the impurities associated with CO2 also get removed. So the question was, which of the following process uses water gas shift reaction for preparation of dihydrogen on a large scale? It is Bosch process. H₂O₂ cannot act as oxidizing agent, reducing agent, dehydrating agent, or acid. Now, H₂O₂ is hydrogen peroxide which contains O-1, and whenever an element has an oxidation state in the middle, it can undergo both oxidation as well as reduction, thereby behaving as oxidizing as well as reducing agent. So in peroxide, the oxidation state of O is -1, which can either be increased to 0 as oxygen O2 acting as reducing agent or decreased to -2 as water acting as oxidizing agent. It also acts as a bleaching agent because it has a good source of oxygen, and H₂O₂ is a weak dibasic acid because it can release two H+ ions. So out of the options given, H₂O₂ cannot act as dehydrating agent. Which of the following metal does not produce dihydrogen gas with dilute HCl? Now, metals have a tendency to react with the acid and release the hydrogen gas, but this release is possible only if the metal is placed above H in the reactivity series. Options: magnesium, zinc, silver, barium. So, the metals which are lying below H in the metal reactivity series cannot displace H from the acid as they are less reactive than hydrogen. Some of these metals are Ag, Hg, Cu, platinum, gold. So just remember that Ag, Hg, Cu, platinum, gold, which are less reactive, can't displace the hydrogen from the acid. Hence, out of the options given, the answer is silver. Ortho and para hydrogen differ in atomic number, atomic mass, nuclear spin in two atoms, or electron spin in two atoms. Firstly, let's discuss about ortho and para hydrogen. Ortho and para hydrogen are spin isomers of molecular hydrogen, that is H2. So these are two hydrogen atoms joined by a covalent bond. Now here the nucleus can have a spin in the same direction or in the opposite direction. When the nucleus spin is in the same direction, it is referred as ortho hydrogen, same direction, orthohydration. This is also called parallel spin. And here when the nucleus spins in the opposite direction or in anti-parallel direction, it is called para-hydrogen. So ortho and para-hydrogen are simply the nuclear spin isomers. Ortho refers to same direction spin, para refers to opposite direction spins. Now few of the important points related with ortho and para-hydrogen. Ordinary dihydrogen is an equilibrium mixture of ortho and para-hydrogen. At 0 Kelvin, hydrogen contains mainly para-hydrogen, which is more stable. At 0 Kelvin, hydrogen contains mainly para-hydrogen, which is more stable. At the room temperature or very high temperature, the ratio of ortho to para hydrogen is 3:1, meaning 75% of ortho and 25% of para. So it has been possible to get pure para-hydrogen by cooling ordinary gas to a very low temperature, close to 20 Kelvin. But it is never possible to get a sample of hydrogen containing more than 75% of ortho hydrogen because the proportion is 3:1 and even at a very high temperature it is almost found to have the same ratio. That's why pure para-hydrogen can be obtained to the extent of maximum 25% or we can't get the ortho hydrogen more than 75%. So ortho and para hydrogen differ in nuclear spin in two atoms. Which of the following hydrides are non-stoichiometric in nature? Ionic hydrides, molecular hydrides, interstitial hydrides, or covalent hydrides. The ionic or saline or salt-like hydrides are obtained from S-block elements and these have a correct stoichiometry, meaning they are stoichiometric hydrides. Molecular and covalent hydrides are one and the same and these are obtained from the P-block elements and they are also stoichiometric. But interstitial hydrides are obtained from D and F block elements and they don't have a perfect stoichiometry, meaning there is a deficiency with respect to hydrogen. So the non-stoichiometric metallic hydrides are interstitial hydrides obtained from D and F block elements. What is false about heavy water? Heavy water is nothing but D2O or deuterium oxide. It is used as a moderator in nuclear reactors. Yes. It can be prepared by exhaustive electrolysis of water. That is how heavy water is actually prepared. Correct statement. It is obtained by fractional distillation of water. False. It can't be obtained by fractional distillation of water or just boiling the water. It needs to be prepared by exhaustive electrolysis. H₂O₂ has higher dielectric constant than D2O. Very correct. In fact, out of all the properties of ordinary water and heavy water, the only property in which water dominates over heavy water is dielectric constant. Water has higher dielectric constant than heavy water. Other properties like melting point, freezing point, boiling point are all higher for heavy water and not for ordinary water because of higher molar mass. Heavy water is more associated than ordinary water? Yes, because heavy water has high molar mass, so the H bonding or the D bonding is stronger, and that's why the heavy water is more associated than ordinary water. So the correct answer is it is obtained by fractional distillation of water. The reagent commonly used to determine hardness of water titrimetrically is. Via titration method, the hardness could be determined by oxalic acid, disodium salt of EDTA, which is nothing but ethylene diamine tetraacetic acid. Ethylene diamine tetraacetic acid. Sodium citrate, the salt of citric acid, or sodium thiosulfate. Now, disodium salt of ethylene diamine tetraacetic acid, that is EDTA, has been used for estimation of M2 plus ions like Mg2 plus Ca2 plus, which is present in hard water, by complexometric titrations. In this titration, what happens is the indicator ions D3 minus ions form red metal indicator complex Md minus with the magnesium or calcium ions. This is a reaction. The magnesium or calcium ion gets titrated with the magnesium or calcium ions gets combined with the D3 minus anion of indicator, which is blue in color. In the basic medium, it forms Md overall minus, that is M2 plus and D3 minus, the overall charge is minus 1. So this metal indicator complex is red in color. Now this complex gets combined with EDTA4 minus, that is ethylene diamine tetraacetate anion, and forms a metal EDTA complex of the type MEDTA overall 2 minus, and the D3 minus ion gets regenerated. But in this process, the red colored complex changes to blue color because of the regeneration of the indicator ion. So the release of the free indicator ion is marked by a change from red color to blue color. So the correct answer would be disodium salt of EDTA. So just remember that the reagent commonly used to determine hardness of water titrimetrically is disodium salt of EDTA. The incorrect statement about structure of hydrogen peroxide is: it is planar. No. Hydrogen peroxide is famously an open book non-planar structure. Dihedral angle in gas phase is 111.5 degree. Yes. Dihedral angle in solid phase is 90.2 degree. Yes. In fact, the OOH bond angle in gas phase was lesser as compared to solid phase. It has open book non-planar structure. Yes. So the incorrect statement is it is planar. Next question. In transforming 0.01 mole of PBS to PbSO4, the volume of 10 V H2O2 required will be 11.2 ml, 22.4 ml, 33.6 ml, 44.8 ml. Just look at the question. First of all, we have to relate the reaction of PbS with peroxide forming PbSO4. Then from 10V, we have to find out the actual volume of the peroxide which would be required for this particular transformation. Let's look at the solution. Firstly, PbS reacts with H₂O₂ to form PbSO4 and peroxide reduces to H₂O. The reaction is 1 mole of PbS reacts with 4 moles of H₂O₂ to form 1 mole of PbSO4 and 4 moles of H₂O. So for 1 mole, the peroxide required is 4 moles. Hence, for 0.01 mole of PbS given, the moles of peroxide required would be 4 times of 0.01, that is 0.04 moles. So with the 0.01 mole information, we calculated the moles of H₂O₂. Next, the 10V H₂O₂ is given. From that, we can relate the molarity by the volume strength relation. The relation is molarity of 10V H₂O₂ is volume strength upon 11.2. So the 10V divided by 11.2 gives a molarity of 0.893 molar. Now, if we have the moles and molarity, we can find out the volume of peroxide with a simple relation of molarity. So therefore, volume of H₂O₂ required is equal to moles divided by the molarity. So the moles is 0.04, molarity is 0.893, and the ratio gives 0.0448 liters or 44.8 ml. So the correct answer is 44.8 ml. In which of the following reactions peroxide acts as a reducing agent? So there are 4 reactions which are given and we have to identify in which of these peroxide would be acting as a reducing agent. Now the shortcut trick for this particular question is when peroxide acts as a reducing agent, it itself undergoes oxidation. So the -1 of peroxide would change to 0, meaning there will be liberation of O2 gas. So just out of the 4 reaction, the reaction which has O2 would be the answer, because in these reactions the peroxide undergoes oxidation and behaves as a reducing agent. So the answer is clearly option 2 and 4. That is option C. Next question. Hydrogen peroxide in its reaction with KiO4, that is potassium periodate, and NH2OH, that is hydroxylamine, acts as reducing oxidizing agent, reducing, oxidizing, or oxidizing reducing agent respectively. Now let's look at the reaction. Now in potassium iodide, the iodine is in maximum +7 oxidation state. Hence it can't undergo oxidation but will undergo reduction. So peroxide in this case will undergo oxidation and will behave as reducing agent. So in this reaction, KiO4 reduces with hydrogen peroxide to KiO3, potassium iodide, and peroxide oxidizes to H₂O and O2. And the +7 oxidation state of iodine changes to +5 in iodate. Next, hydroxylamine reacts with hydrogen peroxide. Now here, hydroxylamine gets oxidized to nitric acid and peroxide reduces to water. So peroxide undergoing reduction indicates here it behaves as an oxidizing agent. Oxidation state of nitrogen in hydroxylamine, that is -1, changes to +5 in nitric acid. Hence the correct answer is reducing and oxidizing agent respectively. Option A. Identify the reaction which does not liberate hydrogen. Reaction of zinc with aqueous alkali. It does liberate hydrogen. Because zinc is an amphoteric metal, it reacts with acid as well as base to liberate hydrogen. Electrolysis of acidified water using platinum electrodes. Yes, when water is electrolyzed, H2 is liberated at cathode and O2 is liberated at anode, allowing a solution of sodium in liquid ammonia to stand. Yes, when a solution of sodium is dissolved in liquid ammonia and it is allowed to stand for some time, the sodium reacts with ammonia to form sodamide NaNH2 with the liberation of hydrogen. Reaction of lithium hydride with B2H6, that is diborane. This doesn't liberate hydrogen. In fact, it forms lithium borohydride LiBH4. So this is the reaction which does not liberate hydrogen. The correct statement among 1 to 4 regarding hydrogen as a fuel are. So these are some factual statements which are being given. We need to identify the correct statements. It produces less pollutants than petrol or gasoline. Yes. Hydrogen on combustion would produce only water. In fact, with the impurity of dinitrogen, it can produce oxides of dinitrogen. But overall, the pollutants would be less in comparison to petrol or gasoline. A cylinder of compressed dihydrogen weighs approximately 3 times more than a petrol tank, producing the same amount of energy. This is also a factual statement, and dihydrogen, because of smaller size and weak van der Waals forces, it will be very difficult to compress it to a greater extent. And that is why the cylinder of compressed dihydrogen would weigh 30 times more than a petrol tank, producing the same amount of energy. Dihydrogen is stored in tanks of metal alloys like NaNi5. Yes, this is also a correct statement. On combustion, values of energy released per gram of liquid dihydrogen and LPG are 50 and 142 kilojoules respectively. This is a false statement because the values given should be interchanged for this statement to become correct. Meaning, the values of energy released per gram of liquid dihydrogen is 142 kilojoule and for LPG it's 50 kilojoule respectively. In fact, the energy released per gram of liquid dihydrogen or even gaseous dihydrogen is about 3 times more than the other fuels like LPG, octane. So the correct statements are 1, 2 and 3. That's option C. The hardness of a water sample in terms of equivalents of CaCO3 containing 10 raised to minus 3 molar calcium sulfate is. Calcium sulfate molar mass is 136 gram per mole. So this is a question related to estimation of hardness of water. The options are 90 ppm, 100, 50 and 10. Let's look at the solution. So 10 raised to minus 3 molar calcium sulfate means 10 raised to minus 3 mole is present in 1 liter of solution. Now here, instead of solution, the solvent is directly considered. If you look at the values of the molarity, it is very small, meaning the amount of solute present in the solvent is very small, and that's why the overall solution can be considered to be equivalent to solvent. That's why the 10 raised to minus 3 molar calcium sulfate indicates 10 raised to minus 3 moles of calcium sulfate is present in 1 liter of overall solvent, as the solute is negligible. Or 136 times 10 raised to minus 3 grams. The moles is converted into mass by multiplying 136, that is molar mass. So 0.136 gram is present in 1000 ml or 1000 gram of water, because water has a density of 1 gram per ml, so 1000 ml is equivalent to 1000 gram. Now we have to convert the calcium sulfate into equivalent amount of calcium carbonate. So 1 mole of CaSO4 is equivalent to 1 mole of CaCO3. That's why 136 gram is equivalent to 100 grams. So 0.136 gram would be equivalent to 0.1 gram. Hence, we can say that 0.1 gram of CaCO3 is present in 1000 gram of water. Now we have to determine the hardness in terms of parts per million. So we have to consider 10 raised to 6 grams of water. So if 0.1 gram is present in 1000 gram, in 10 raised to 6 gram, it will be 0.1 into 1000, that is 100 gram. So overall, when 100 gram of CaCO3 would be equivalently present in 1 million 10 raised to 6 gram of water, the hardness of the water in ppm would be equivalent to 100. So the correct answer is option B, 100. The strength of 11.2 V solution of H₂O₂ is. Now, the strength of 11.2 V solution means we have to find out the amount of peroxide in gram per 100 ml, because it is the percentage strength which we need to identify. Hence, option given are in percentage: 3.4, 34, 13.6 and 1.7. So let's look at the solution. Now when the volume strength is given, we can convert it to molarity by using the relation of volume strength upon 11.2. Hence the 11.2 volume strength upon 11.2 gives you 1 molar of H₂O₂. This 1 molar of H₂O₂ means 1 mole of peroxide equivalent to 34 grams of peroxide present in 1000 ml. But the percentage strength is to be indicated in 100 ml. So if 34 gram is present in 1000 ml, 100 ml would contain 3.4 gram. So this 3.4 itself is the percentage strength of the 11.V solution of peroxide. Hence the correct answer is option A. In comparison to zeolite process or permutate process, for the removal of permanent hardness, the synthetic resin method is less efficient as a resin cannot be generated. No, in fact, the synthetic resin method is more efficient because it can exchange both cations and anions. And in zeolite as well as synthetic resin method, the resin could be regenerated in both the processes. More efficient as it can exchange only cations? No. More efficient as it can exchange both cations and anions? Yes, this would be the correct answer. Less efficient as it can exchange only anions? No. Now we move to multiple answer correct type MACT questions. What is false about ice? So some factual statements about ice are being given and we have to identify the false statement. It has 3D hydrogen bonded open cage like structure. Yes. It has less density than water. Yes, that is the reason it floats on water. And the reason was related with the interstices or gaps which are present in the 3D structure. Each oxygen is surrounded tetrahedrally by 4 other oxygen atoms. Yes, in the 3D structure, each oxygen is surrounded tetrahedrally through sp3 hybridization by 4 other oxygen atoms. Each oxygen atom has 4 hydrogen bonds around it. False. Because each oxygen atom in the 3-dimensional structure of ice is surrounded with 4 hydrogen, out of which 2 are normal bonds of H₂O and 2 will be hydrogen bonds. So it's not 4 H bonds, it's 2 H bonds. That's why the false statement about ice is option D. Among the hydrides given below, which are reasonably good acids? Ammonia, which is a covalent or molecular hydride. Hydrofluoric acid, again a covalent or molecular hydride. HN3, that is hydrozoic acid, again a covalent or molecular hydride. NaH, which is ionic or saline hydride. Now, for any compound to behave as a good acid, it should be able to release H plus and the anion formed should be highly stable. In case of ammonia, the nitrogen has a lone pair and it will have a tendency to accept H plus, so it will behave as a base. HF is a good acid because it can give away H plus easily due to the formation of a stable fluoride ion. HN3 hydrozoic acid is also a good acid because after the release of H plus, the N3 minus or the azide anion is stabilized by resonance. And sodium hydride has H negative and not H plus. So the good acids out of the options given are HF and HN3 hydrozoic acid. Fe3 plus is reduced to Fe2 plus by using. This is a question of JEE-Advanced 2015. Let's look at the options. H₂O₂ in presence of NaOH, Na2O2 in water, H₂O2 in presence of H2SO4, Na2O2 in H2SO4. Now if we look at the options A and B, they are actually equivalent options. H₂O2 in presence of NaOH and Na2O2 in water are equivalent because when Na2O2 dissolves in water, it forms sodium hydroxide and hydrogen peroxide. Similarly, options C and D are equivalent. H₂O2 in presence of H2SO4 and Na2O2 in H2SO4. Na2O2 dissolves in acid to form Na2SO4 and H2O2, and with the excess of sulfuric acid, the peroxide would be present in acidic medium. So basically, we have to identify whether the reduction is possible in alkaline medium or acidic medium. Now this can be analyzed by the standard reduction potential or the SRP values, the concept of which is discussed in electrochemistry. Have a look at the solution. The reduction of ferric to ferrous is possible provided reduction potential of ferric to ferrous is larger than reduction potential of peroxide. To understand this, we need to understand the standard reduction potential values. Ferric reduces to ferrous with the SRP value of 0.77 volt. Peroxide in acidic medium has SRP of 1.77 volts and O2 in aqueous medium reduces to peroxide and 2OH minus, meaning the alkaline medium has SRP of minus 0.15 volt. So the reduction is possible only if the ferrous to ferric SRP is larger than the reduction potential of peroxide. So if we observe for acidic medium, the reduction potential is much higher. So the reduction won't be possible in acidic medium. But peroxide in alkaline medium has a lower SRP. So here the reduction will be possible only in alkaline medium. So it follows that peroxide is a more powerful reducing agent in alkaline medium as compared to acidic medium. And therefore Fe3 plus is reduced to Fe2 plus by alkaline H₂O2. And as I discussed, Na2O2 in water is equivalent to NaOH and peroxide. Also, the net reaction would be, if we reverse that reaction, H₂O2 in alkaline medium, we get the SRP of 0.15 volt. The negative will change to positive. And the overall reaction of ferric with peroxide in alkaline medium giving ferrous and O2 and 2H2O will have the E0 value positive of magnitude 0.92 volt, indicating that the reaction is feasible or possible. So Fe3 plus would be reduced to Fe2 plus only by peroxide in alkaline medium, and that's why the correct option will be A and B. What is true about saline hydrides? They are binary compounds of metal and dihydrogen. Yes. They are crystalline and non-volatile. Since they are ionic hydrides, they are crystalline in nature and they, ha they have a high boiling point, due to which they are very less volatile or non-volatile. Their melt liberates H2 gas at cathode. No. Their melt will have the hydride ion as H-, which will move towards the anode and undergo oxidation and will liberate H2 gas at anode and not cathode. So this will be a false statement. LiH, BeH2 and MgH2 are covalent hydrides. Yes, because of high polarizing power of lithium plus, beryllium 2 plus and Mg2 plus, the hydrides of Li, Be and Mg are found to be covalent as per Fajan's rule. So the true statements are option A, B and D. Thank you.